I'd like to show you how to work through the analysis of an air conditioner problem from start to finish, complete with all the numbers worked out. And this is a classic solution to problem 1020 in your textbook. So let's see, chapter 10. Chapter 10 is about refrigeration cycles, of which air conditioners are part of it. I got to tell you that this problem 1020 is a classic analysis that if you can hang in there and understand what's going on in the solution of this problem, which is not trivial, you are going to be well positioned to basically master most of the material covered in 1020, and it's going to help you prepare yourself to do well on a quiz related to chapter 10 or a test problem related to any kind of refrigeration cycle. So I hope you hang in here with me. I'm going to do my best to show you how to solve this problem 1020 from start to finish, complete with numbers. Okay, and here we're going to blaze through this and then get off track a second, but here's the problem statement. It says the window-mounted air conditioning unit that you're seeing with your eyes supplies 19 cubic meters per minute of air at 15 degrees C and a pressure of 1 bar to a room. 1 bar is about 1 atmosphere. Air returns from the room to the evaporator of the unit. What's the evaporator? At 22 degrees C. The air conditioner operates at steady state, okay, on a vapor compression refrigeration cycle. Wonder what that is. With R22 entering the compressor. What's the compressor? At 4 bar and 10 degrees C. It says saturated liquid refrigerant at 9 bar leaves the condenser. What's the condenser? The compressor has an isentropic efficiency of 70%. Okay, efficiency, we know that. And refrigerant exits the compressor at 9 bar. Again, exits compressor, what does that mean? 3 things to determine in this homework problem. Determine the compressor power, the refrigeration capacity in tons, and the coefficient of performance. And so, look, if you are a formula person, you're sunk. There's no list of formulas in the book that's going to deliver you to the promised land on this problem that I would consider it has a degree of complexity to it. So don't let anybody convince you that this homework problem is easy. I'm going to try to work you through it step by step. But first, some background and fundamentals. If you're not interested in the background and fundamentals, you can jump ahead, but would like to cover as quickly as I can. Common Sense 101. What do you see with your eyes when you look at a window air conditioning unit, which is our homework problem? I see this. Okay. Maybe I want to get a little more. I dove down into Home Depot. You can buy a window air conditioning unit from Home Depot, Lowe's, and many, many other retail stores. So I clipped out some things from Home Depot. And in particular, here's a chart that says, well, what do I need? What size window unit do I need? Well, it depends on the cooling square footage you need or the area of your room. And here's a table, and it says, well, 8,000 BTUs. I got to tell you, that's jargon. So be very aware, very important that Home Depot and all these other retail places, when they say 8,000 BTU, that's not engineering units. What this really, it's a jargon shortcut for BTUs per hour, BTUs per hour. So out in the real world, when you see a window unit, 8,000 BTUs, in your engineering mind, 18,000 BTUs per hour. How do I know that? Well, my instructors, when I was an undergraduate, explained that to me, but also an important term, this 12,000 BTUs. Well, that's really 12,000 BTUs per hour. And it turns out that the units of cooling can also be expressed in terms of a ton of cooling that I explain a little later in other videos. But that's important. That's an important conversion factor that you're going to need to understand what is a ton of cooling in your homework problem. Okay. Here's a big picture of the window air conditioning unit. Let's keep working on what do you see? What do you see with your eye when you are looking and studying with an engineering eye at a window air conditioning unit? Well, the first thing I see is this nice, cool supply of air coming into the room that's keeping me nice and cool. That's the first thing I see for my comfort. That's for the second thing I see. I see an electric power cord coming out of this window unit, and I got to plug it into the wall for it to work. So another thing to observe is electric power is required to run the compressor part of this window air unit that's somewhere in this box. That's second thing. The third thing I see when I look at the window unit is there's a bunch of louvers down here, and sort of as an engineer or even as a child, I put my hand up. Oh, that's where the warmer air is coming back from the room. It's warmed up because of heat transfer, and that's what's being cooled down. It's being cooled down to supply nice cool air for me to be comfortable. So that's the third thing I see. And then if I were to walk outside, I'd see this whirring box, but also I would observe, if I got close to it, I would observe sort of hot air, heat being rejected from this box out to the surroundings. Now, do be aware that if there's air blowing out on you and it's kind of warm, it has nothing to do with what's going on in here inside your house. But do recognize that heat is being rejected to the outside surroundings. That's an important part of the air conditioning unit. Okay. You got all that. You say, why is this guy telling me so? I know all this stuff already. It's good. This is going to help us fully understand what's going on in this air conditioner unit box. Oh, some other equipment, a little more modern, wall mount air conditioner. Well, a little harder to figure out because look, at these wall mount units, about all I see when I'm looking is cool air supplied to the room, and that's about all I see. Now, this young lady here, she's got the remote control, so she's controlling the power and the thermostat and things like that. But a little harder to study on the wall mount air conditioner, but it works exactly the same. Here's even a newer sort of technology that I'm seeing. It's really kind of neat. And for me, I'd say it's more attractive than a window mount air conditioner. It's called a portable air conditioner. And here's the box. And notice here, it's rated at 8,000. Oh, look at that. They got the units right. BTUs per hour. Good for them on the LG box. 8,000 BTUs per hour. That's correct. Okay. What do we see with our eyes here? Well, one thing we see first, cool air is supplied to this room from the top of this box, keeping me comfortable. That's nice. Okay. If we look on the side of the box, we see some more louvers. That's the return air of the warm air from the room to be cooled down. And another thing we see from this portable air conditioner is there's this duct. To me, it looks almost like a dryer duct, but it's hooked up. It's blowing hot air, rejecting heat to the outside surroundings. And so do you see how similar this portable air conditioner is to the window air unit? But I'd say much more attractive and much more portable. Automotive air conditioner, when you're in your car and the car is hot and you want to get cooled down, all you're interested in seeing and feeling is this nice cool air coming out from your dashboard. So that's really what you see. But do recognize that the air conditioning unit is up in the front of your car, and so there is return air from your cabin probably going somewhere underneath your dashboard. There's return air to be cooled back, and also heat is rejected to the surroundings from the condenser coils that's located somewhere in the front under the hood of your car. So just do be aware of that. Now, all four of these examples have something in common. What they have in common is the basic vapor compression refrigeration cycle that is chapter 10, your chapter 10 in your textbook. So that's what all of these easily purchasable pieces of equipment have in common. They all run on the basic vapor compression refrigeration cycle, and that's what this homework problem is all about. 4 basic components of the basic vapor compression refrigeration cycle. A compressor, it needs power to run. It's compressing refrigerant vapor to a much higher pressure. Okay. A condenser, that's where the hot is. The hot vapor is being condensed in the condenser. This is nothing more than a heat exchanger, and it's exchanging heat with the surroundings. So there's my red arrow. That's heat transfer to the surroundings. And expansion valve, it's nothing more than a restriction in the refrigerant line. It's just a little opening that's a valve, just a little tiny opening where the high pressure is being reduced to a lower pressure. And that's what caused the refrigerant to get really, really, really cold. Okay. Oh, condensed refrigerant comes out of the hot condenser. So state three, it's going to be hot, but it's going to be a liquid refrigerant. Goes through the expansion valve, high pressure to low pressure, really, really cold mixture comes out, and that really, really cold mixture goes into the evaporator section, and that's where you're going to get your cooling from. Okay, back to our homework problem. There's the basic vapor compression refrigeration cycle. So again, let's review what's our homework problem that we have to solve. We've got R22. That might be a little different than most of your homework problems so far that have been R134A, so do be aware of that, okay? You're asked to find three things: compressor power, refrigeration capacity in tons, and the coefficient of performance of the window air conditioner unit. There's some things you're given. So as we look through the problem, you're given the volumetric flow rate of air that's coming to you. Okay. Volumetric flow rate of this air coming to you. Also, the warm air return coming back to this air conditioner unit, 22 degrees C, and the cool air blowing in your face, 15 degrees C. That's going to be golden information to get you moving on the problem. And also, I've gone to the back of my book and I've copied 1 ton of refrigeration. That's what we got to get in our problem assignment, is equal to, well, 200 BTUs per minute. That's 12,000 BTUs per hour. But for our problem, key is 211 kilojoules per minute. 211 kilojoules per minute is 1 ton of refrigeration. Okay, now let's get moving. That's your background, some little historical background, getting units straight. Now we're going to move on to the numerical solution. Let's start with a basic schematic. Always start with a sketch. Well, a lot of students have trouble even getting this type of sketch down. Notice we don't have any state numbers. It's a little murky. We're going to get more definition, but at least let's understand what we've got here. Up here, we've got a system operating in a cycle that you've covered in a refrigeration cycle. You covered in chapters 5 and 6. 5 and 6, more than chapter 10. 5 and 6, you covered this. The working fluid in this black box refrigeration cycle is refrigerant 22. Properties in the back of the book. Okay. What else do we have in our sort of schematic? We've got air. We've got air that's coming back from the room that's warm. It's being cooled down in a black box, and it's coming back out cooler and making you comfortable. So moving ahead, this is this isn't intuitively obvious. Here's what we're going to find in our solution in this order. We're going to first find the cooling capacity. We're going to discover that the air, analyzing the air system, is the key to this. Cooling capacity, get that first. Next, we're going to determine the compressor power, the electric power it takes to run the compressor. And then last, it's going to be the coefficient of performance, COP, or beta. That's incredibly easy. That's the energy sought over the energy that costs. Energy sought, cooling capacity. Energy that costs us, the electric power to run the compressor. So COP we're going to get that in a snap. Okay. So that's our roadmap. Now, starter kit. I said, if we study on this enough, if you're an experienced engineer, if you've solved hundreds of these types of problems, you kind of know where to start. If you're a student and you've never solved one of these problems, you don't know where to start. Unless you're just incredibly insightful, and I congratulate you on that. But here's the starter kit on the air. Look, when we study this air situation, we've got the volumetric flow rate. Well, can we get the mass flow rate if we've got the volumetric flow rate, 19 cubic meters per minute? Well, yeah, we can calculate the density of air. We can do that from the third week of class. If we've got the density of the air and the mass flow rate, we can and the volumetric flow rate, we can calculate the mass flow rate. Look, if we've got the inlet and outlet temperature of an ideal gas, we can calculate the heat transfer using the first law. The heat transfer from the air into the evaporator, because do you see that the amount of heat transferred out of the air, it's got to go somewhere, so it's got to go into the evaporator. So that's our starter kit, working on the air first. Do not be embarrassed if you didn't see where to start. Just going to try to, once you work through this, you're going to get better and better at this. And by golly, you certainly will be a lot more prepared to take a quiz, a test, or exam. Okay, now let's draw a formal sketch of what I had in that schematic. Okay, and so here's a formal sketch. I've taken a screenshot of the basic refrigeration cycle. I've labeled the states consistent with your textbook. 1, going into the compressor. 2, leaving the compressor, going into the condenser. 3, a liquid refrigerant leaving the condenser. It's hot, a hot liquid, leaving the condenser, coming into the expansion valve to state 4. Pressure's dropping, getting really cold. Cold refrigerant mixture goes into the evaporator, process 4 to 1. Okay, so 1, 2, 3, 4, that's the refrigeration process. Now, I've also got air in my window air unit. I've labeled that 5 to 6. 5 to 6, I've got the ideal gas air. I'm showing a heat exchanger coming in at 22 degrees C, cooling to 15 degrees C, and I've labeled 19 cubic meters per minute. Let's look at the given information for the basic refrigeration cycle. You're given inlet compressor, 4 bar and 10 degrees C. Hey, here's a hint. When you have a phase change substance and you're given the pressure and temperature, it's very probable that you're going to be a superheated vapor of that phase change substance. Typically, if you're given a pressure and temperature of a phase change substance, chances are mighty good for this kind of situation, you're going to have a superheated vapor. Superheated vapor. Now, let's see, you're given that the compressor efficiency is 0.7. I've written that down. I've written 9 bar down, but that was not stated in the given information. What was stated is what's coming out of the condenser is a saturated liquid at 9 bar, and I wrote that down on my sketch. When I read chapter 10, I see that the condenser is a heat exchanger operating at constant pressure. And so if the outlet pressure of the condenser is 9 bars, the inlet pressure of the condenser is 9 bars. So that's why I wrote down 9 bar there. Okay, state 4, don't know anything about that right now. And then I've got I think I've already talked about the given information for the air. Volumetric flow rate given, inlet and outlet temperature given. It's a heat exchanger. Where do I start? Again, do not be embarrassed. That's a lot of given information. Where do I start? Oh, I know why I wrote that big red box. If you say, where do I start? I'd better go to the book and I'd better start looking for formulas. This is a complex problem. I need to write. I've got to start with formulas. That is a losing proposition for this problem. Okay. Looking for formulas is not going to win the day for you. You're welcome to look as much as you want, but this is a great and classic problem because you as the engineer have to study on it, study the given information, and you have to see with your eyes that the place to start is analyzing the heat transfer from the air. And I have enough information to determine the heat transfer from the air. Then, if I've got the heat transfer from the air, it's going into the evaporator, so that's good. That'll get me a third of the way through. But once I get the heat transfer going into here, then I can calculate a mass flow with a refrigerant, and then go from there. The next thing I do in my solution is draw a TS diagram of the refrigerant R22 only. This has nothing to do with air. This is purely process 1, 2, 3, 4. It relates only to this basic refrigeration cycle that's giving us the air conditioning. And this is going to help us visualize what we've got when we look up properties. Say, you know good and well, we're going to have to look up enthalpies. We're going to have to look up H1. We're going to have to look up some H's at state 2. We're going to have to look up H value, enthalpy, state 3, and state 4. This is going to help you keep straight. So this is why, I've drawn state 1 as slightly superheated vapor, okay? The compressor, it's increasing the pressure. That helps you visualize that coming out of the compressor, you have a superheated vapor. So you don't have to memorize it. You have to look at the TS diagram to see, oh, I see, I've got a superheated vapor coming out of the compressor. The condenser, well, the word says it all. It's condensing a vapor. And in the problem statement, it says you're condensing down to saturated liquid at 9 bar. And so that's what enables you to put your dot right there on the left-hand side of the dome at saturated liquid. State 4, I've studied enough to know that the throttling valve is a very irreversible process. There's no power coming out of that valve. We're not getting any work out of the valve. The valve is fully insulated. And so process 3 to 4 is shown as a dashed line, very irreversible process going through the expansion valve. So this has a lot of value in your solution. So this is part of a thorough solution of this classic problem. TS diagram for the refrigerant only. Okay, I hope I've convinced you to start with the airflow first. That's gonna be the starter point where we're determining the refrigeration effect. In other words, how much is the air cooling down? Refrigeration effect is how much heat is the evaporator absorbing. And so this is almost like a little homework problem unto itself, okay? It's not trivial. So let's go through the process of analyzing the airflow to determine the heat transfer from the air. Okay, so notice here in my sketch, I've drawn a separate sketch. Q dot into the air is less than 0. He's not flowing into the air, it's flowing out of the air. Q dot into the air is less than 0. W dot out, well, there's no work. The air heat exchanger is not lifting a weight. W dot is 0. Okay, so there's my sketch. It's a pretty decent sketch of given information. I'm going to treat air as an ideal gas with constant specific heat. Got to look up C sub P. Part 2, determine the density of the ingoing air. Rho is P over RT, or V is simply RT over P. V is RT over P. Get specific volume. Step 2. Volumetric rate is given. So therefore, the mass flow rate is rho times AV. Rho, the density, times the volumetric flow rate, AV. Or, if you learned it the other way, it's the volumetric flow rate, AV, divided by little v, whichever you prefer. Fourth, the first law for an open system, one inlet, one outlet, steady state, steady flow, ideal gas, temperatures are known. So Q dot into the air, it's going to be a negative number, minus W dot out, that's 0, equals M dot of the air, just found it, CP of the air, got to look it up, times delta T of the air, T2, 15, minus T1, or T6, 15, minus T5, 22. Got it? Okay. That's how we're going to calculate the heat transfer rate. How do I get CP of the air? Well, if I don't know it, I go to table A20 and I pick 300 degrees K, which is a representative temperature. We're going to hold it constant and see that CP of the air is 1.005 kilojoules per kilogram degree K. Depending on your class, I guess you could also go in and look up H values at those two temperatures. In engineering practice, for atmospheric air, this is the way we do it. Constant specific heat for air at a representative temperature. CP 1.005 kilojoules per kilogram degree K. Okay, so let's go and determine the heat transfer rate. Let's see, the first thing we do, we write down R and CP, R for air and CP for air, okay? Volumetric flow rate. We calculate rho. Rho is P over RT. Okay, let's see, the air pressure, 100 kPa. Okay, let's see. Gosh, did I not, that might not have been given. No, I think it was. I think it was said atmospheric air was at 1 bar. Okay, so air pressure 100 kPa, that's 1 bar. Okay, so rho, the density 1.21 kilograms per cubic meter. And so the air mass flow is rho times AV. AV is 19 cubic meters per minute. Here it is, cubic meters per minute, 19. 22.987 kilograms per minute airflow. Okay, and so now we're going to apply the first law. There's my yellow is my input numbers. So I'm going to apply the first law. Now, I've kind of written it out in Excel. I've also written it out here in a text box. Q dot into the air, it's going to be a negative number, but it looks like I've made that adjustment over here in Excel. M dot of the air, got it. CP of the air, got it. Delta T of the air. So the air cooling effect is 161.71 kilojoules per minute, negative 161 into the air. So air is rejecting heat. Oh, and so that's what's going into the evaporator. My conversion factor, I've got a screenshot of that. Conversion factor and so that's kilojoules per minute here, 161.71 kilojoules per minute. Got to get my units straight. 211 kilojoules per minute is 1 ton. And so my refrigeration capacity, what's going into the evaporator from the air is 0.766 tons of cooling. Yay! We're 1/3 of the way done. It's going to go a lot faster from here. We're 1/3 done. 0.766 refrigeration capacity or cooling capacity. That's the cooling effect. The next thing let's do is figure out the refrigerant flow, the rate at which the refrigerant is going around and around and around in this cycle. What we're going to do is use the first law for the evaporator process, for process 4-to-1. 4-to-1 in the evaporator process. TS diagram, state 4 to state 1. And so let's see, can you think of, now, so we've got Q dot N, don't we? We've got a number for this. What's the first law for the evaporator? Q dot N, got it, minus W dot out, 0. The evaporator's not lifting a weight, equals M dot of the refrigerant, don't know it, times the enthalpy change, H1 minus H4. If we can get numerical values for H1 and a numerical value for H4, we can calculate the mass flow rate of the refrigerant. Let's do that. Okay, here's our first law that I just said in words. Okay, here's my sketch for the evaporator. Here's check, I know it. Okay, first law, Q dot N, know it. W dot out, nothing. M dot, that's what we're looking for. H1, it's refrigerant R22, 4 bar and 10 degrees C. We will look that up in the superheated tables. We're going to get a number for that. H4, we got to figure out what H4 is. Oh boy. So we're going to get off track here a second. We've got to back up a little bit and go to the expansion valve. And we're going to write the first law for the expansion valve. We got a new sketch. So we're getting in the weeds a little bit here. Okay. Here's my sketch for the expansion valve, process 3-to-4. Okay. Fully insulated expansion valve, Q dot N is 0. Is the expansion valve lifting a weight? Nah. W dot out, 0. Okay. So let's write the first law for the expansion valve. Q dot N, 0, minus W dot out, 0, equals M dot, don't know it yet, times H4 minus H3. Well, look, left-hand side is 0. Divide both sides by M dot that you don't know, and this happy result is H4 equals H3. So can I get a numerical value? If I've got a numerical value for H3, I've got therefore a numerical value for H4. Let's keep plugging ahead. Back to numbers. Let's find H3 first at the top of the slide. H3, it says it's saturated. Let's go back a slide. H3, it's a saturated liquid at the condenser pressure given. Condenser pressure 9 bar. All right, here we go. We go to the pressure table. This is what we know. Saturated refrigerant, R22. We come down to 9 bar. Saturated liquid, enthalpy, H. We write down 68.59. That's H3. Well, look at my solution in Excel. H3 equals H4. We just showed that, okay? H4, 68.59. Yay. State 1. It's going to be superheated vapor. We know the pressure and we know the temperature, so we'll go to the superheated table, R22, and we're going to look up H. We'll write down 259.18 in our solution. Now, looking ahead, because I've done these problems a few times, you're going to learn that when you're analyzing a compressor, you need the inlet entropy as well as the inlet enthalpy. So let's also write down, we're going to need it, so let's write down S1, now that we're looking at it with our eyes, 0.9795 kilojoules per kilogram degree K in our solution, because we're going to need S1. So we're planning ahead. We're writing down S1 as well as H1. But look, what were we trying to do? We're trying to study the evaporator, but now we do have H1 and we have H4. So now we got down to the weeds. Now we can move forward again. We were looking to find the refrigerant mass flow rate. Okay, so now here we go. We've got H4 as a number, 68.59. We've got H1, 259.18 kilojoules per kilogram. Okay, we've got Q dot L. We've got the rate at which heat is added to the refrigerant in kilojoules per minute. And so we've got M dot of the refrigerant, one equation and one unknown to get 0.848 kilograms per minute. Okay. Say, well, why did we do that? Well, we need the mass flow rate for the refrigerant in order to apply the first law to the compressor. So are you starting to see why just looking for formulas in the book is not going to win the day for you? You've got to think through the analysis steps here rather than just writing formulas down. Okay. We found M dot of the refrigerant, 0.848 kilograms per minute. Now we're on to the compressor because we got our assignment. How much power does it take to run the compressor? The first thing we're going to do is write down the first law for it. We know the compressor is adiabatic, but not reversible. Compressor is adiabatic and irreversible, but to win the day, but we know the compressor efficiency, so we have to first study the isentropic reversible adiabatic compressor power needed. Let's write the first law. Q dot into the compressor, zeros, adiabatic, minus W dot out. That's what we're looking for. M dot, we just found it. H2 isentropic, H2I. Okay. We need to figure out, we're going to figure that out, a number for that somehow, but H1 we have a number for. We've already found it. Okay. I wrote down the first law for actual just so you can see the difference in the two statements of the first law for two different processes. This is irreversible and adiabatic. This is reversible and adiabatic. We're going to focus on the isentropic compressor. Then we will apply compressor efficiency to get the actual power needed. All right, so let's figure out H2 isentropic. Here's my TS diagram from previous work that you would do in pencil and paper. We're looking to find out what is this H2I or 2S in your textbook. What is H2S? How would we do that? Well, let's see. We logged in S1 earlier to plan. S1 is 0.9795 kilojoules per kilogram degree K. And for the isentropic compressor, that exactly equals S2I. Okay. Another thing we know about state 2 is that the pressure is 9 bar. Well, that gives us two independent properties at state 2I. We've got entropy and we've got pressure. So the beauty of this sketch is it shows us we're in the superheated phase. So that's what tells us we got to go to the superheated tables. We're going to go to 9 bar, and we got to shop around in the S column at 9 bar for the number 0.9795. And lo and behold, for this homework problem, thank goodness, look at this. We've got an exact match. We do not have to interpolate for a temperature or an enthalpy. And so in my solution, I'm able to, do you see how we found this state? We had two independent properties, pressure and entropy, 0.9795. So we're looking for we're looking for H2 isentropic. So in the solution, we're going to write down the number 280.68 kilojoules per kilogram. There it is in my solution. Beautiful, exact match. Woo, we didn't have to interpolate. Very nice of the author to make us a nice, well-contrived problem here. Okay, that's what we're trying to do. We're trying to get to H value for the isentropic reversible adiabatic compressor, because now we can apply the first law for the reversible adiabatic compressor process. All right, so let's see. We've got H2 isentropic, just found it, 280.68. We've got M dot. We already found it, 0.848 kilograms per minute. H1, we've got it, here it is, 259.18. One equation and one unknown, Q dot in, 0, adiabatic, W dot out. It's going to be a negative number. There it is, negative 18.242 kilojoules per minute. Kilojoules per minute, that's our units, okay? Now we're going to apply compressor efficiency because that's given. So remember, compressor efficiency is the isentropic power, just found it, divided by the actual power. Question in the homework problem. So we'll rearrange our definition. The actual power needed by the compressor is the isentropic power divided by 0.7, the compressor efficiency. So let's see, H2I, we just found it. Okay, H1, we've got it logged in. Okay, we found the isentropic power, previous slide, negative 18.242 kilojoules per minute. We divide that by 0.7. It's going to be a bigger negative number. It's going to be more negative. Negative 26.061 kilojoules per minute, but that's not what was requested in the problem. What was requested was kilowatts. Wow, what's a kilowatt? A kilowatt is a kilojoule per second. So if we've got negative 26 kilojoules per minute, we divide that number by 60 to get our unit straight to find that the actual power required by the compressor is 0.434 kilowatts, kilojoules per second. We're 2/3 of the way done now. Wow. Now the third part, coefficient of performance. Woo! We've just about finished it. All we got to do is remember the definition of the coefficient of performance. It's the energy sought over the energy that costs. We've got both of those already. Look at this. So let's see, the energy sought, cooling effect, 161.71 kilojoules per minute. The energy that costs, the electric power needed to run the compressor, 26.06 kilojoules per minute. So that's energy sought over the energy it cost is 6.21. So the coefficient of performance of this air conditioner is 6.21. Okay. Wow, all of a sudden finished. Boom. So that last part went really fast. And that's what reminded me of something as I was preparing this presentation. If this is a quiz, and you say, oh my God, there's so many computations, I'm going to run out of time. I don't have time. I can't get to a number. By golly, at least on your solution, write down the coefficient of performance beta is simply Q dot L, the cooling effect, divided by W dot compressor. That's going to get you a third partial credit simply by writing down what you know without even putting pencil to paper numerically. Okay, so please do be aware when these type of homework problems turn into quizzes and tests, what kind of things do you know off the top of your head that you can write down even if you don't have numbers, where you clearly write down what you're doing, and you might write down don't have time for the number or something like that. Okay, friendly advice. So finished, and then here's our summary. If I'm doing the homework problem to turn in, I'm going to write down the summary results at the bottom of my sheet. Compressor power required 0.434 kilowatts, cooling capacity 0.767 tons, and coefficient of performance beta 0.621. Okay, I hope you got something out of this video in terms of working through the steps. I tried to illustrate the thinking involved to go step by step by step. Clearly, formulas in the book would not have helped you solve this problem at all. So be honest with yourself. There's two ways you could have utilized this video. Method number one, blindly copy down the numbers, blindly copy down the sketches as best you can, turn those answers in for credit, and you're going to get credit, and you're going to get 10 to 15% of your final grade is going to be your homework. Great. But that 90 or 85%, when you're doing the homework, you're preparing yourself to do well on that 85 to 90% of your grade. And so it is my hope that for this chapter 10 preparation, you followed along the video to kind of understand the fundamentals, to see how it hooks up with Common Sense 101 and the thinking process that you need to do to generate your own solution. So that's my hope of the way you utilize this video. Either way works. That's up to you. Now, if you want more details about Chapter 10, recognize that I've got a bunch of presentations that I offer under Chapter Key Points. So Chapter 10's various videos. If you're interested in more of the basics, you want to learn more about a compressor, want to learn more about a condenser, more about expansion valves, evaporator, performing the cycle all alone. Now, this homework solution, I hope, would totally replace the cycle analysis business. If you're feeling comfortable with what you're doing in this homework problem, I think that's great. You will be well prepared to handle any quiz, test, or exam problem associated with Chapter 10, I think. So that's the start to finish solution to 1020. Okay, well, I'm going to save this to the homework solutions playlist, and hope you get a lot out of the homework solutions as well as the background videos.